Hello, welcome to another video for this class. In this video, we are going to study section 4.4 and we just go over some of the logarithmic properties, and we are going to practice those properties in a couple of examples. So far in the previous section, we learned about a logarithmic function and some of the properties of logarithmic function. We have the inverse property, which let me summarize and quickly review these properties. So first of all, let's first review logarithmic function. So we learned that we have the, let's say you have exponential function. So this is exponential function. And by this notation, let me say that here we call B the base, X is the exponent. And so we have base B to some exponent, and this is exponential function. And we said that logarithmic function is nothing other than the inverse function of this exponential function. So when you have logarithm, it's gonna be same base. So what it does is that it takes the input value. So if I want to rewrite this in terms of let's say this is the input and this is the output of this function. So it just switch the input output in the inverse function. So it's gonna take the output and it's gonna return me the input value. And you can also go the other direction. Remember, in the previous section I mentioned always base to the power of this, which is gonna be base to the power of x, should return us y. So logarithm function is nothing other than the inverse function of exponential function. Now there are some properties these properties are going to be very helpful when we deal with solving equation that involves logarithm. So the first property that we learn, so first of all, let me quickly refresh your mind. Log of any number to its base. So that means if you're taking the logarithm of a value to a base and the base is the same as the value. So suppose you're taking a logarithm to a specific base and the input is the same value, then that's always 1. And you can easily verify that. Log go to this way. So what does this mean? It means b, base b to the power of 1 should give me b, which is right, because any value to power 1 is itself. Now, the second property was that if you have exponent, so let's say you're taking logarithm to the base b, and the expression has some exponent. In your textbook, for example, you have b to the x, right? We learned that the exponent can always come and sit as the multiplier of the, so this can be written as x times log of b to the base b. So the exponent can come and sit as the multiplier of logarithmic function. And on top, we just learned that logarithm of b to the base b is gonna be 1. So for that reason, it gives me x. So in other words, we have the inverse property. You see log of b to the x for the base b is x. The second property, let's look at the second property, the next property here. the next property says that if you have base b, so you have b to the power of log of x. So look, here is the setup. You have b to the power of log of x to the same base, same b. Then it says that it's gonna be x. So let's evaluate that. So, right, this is what this says. It says that you have this equation. Let's just quickly verify that. One way to verify this equation, this property, is to take a logarithm of both sides. It doesn't matter what base. You can take any logarithm that you want. So let's take log to the base b and take a log in base b of both sides, right? So now, recall that. So in terms of logarithm, this is a logarithm of this thing. And this is, right. Okay, so I'm going to use the same color. So we are taking the log of left side and we are taking the log of right side. So now, this is this sits as an exponent, right? Recall that it can come and sit as the multiplier. So I can write this as log of x to the power of b times, right, times log of b to the power of b, which is right, which is exactly, look, because this is 1, so this is gonna give me log of x to the power of b. So you can easily verify that, verify these two equation, and also exponential property, which is very useful. I already show you that for logarithmic function, when the input is exponential, that exponent can come and sit as the multiplier for the logarithmic function. And you can also change the base, and if you need to change the base, log of a to the base b can be written as a quotient of log of a over log of b to any base that you want. Okay, so these are not new. We observed these properties in the previous section. But I'm going to introduce two new properties which are very useful and helpful when we solve equation. Sum of log, let's start with sum and difference of log. So sum is that if you are adding two logarithmic expression which have same base, so look, this is the sum property. So sum. Suppose you are adding two logarithmic function, okay? So you have log of, I don't know, a to the base b, log of b in base b. So you see the base is the same. Both of these two have same base. So it's gonna be log of the base of the result should be the same. So you see all of these terms have the same base. Now, the thing is that you have the addition of these two functions. The input is going to be the product of these two values. So if you have like a, and your textbook uses c, so you just multiply them, right? And for the difference, suppose you have log of a in base b, log of b in base b, and instead of addition, you are subtracting them. So the result logarithmic function has the same base. So you see again, all of them has the same base, but the input value is the quotient, is the division of those values, a over b. And I'm going to show you the application of these properties in a moment. So look at example 1. So we have this expression. This expression contains three logarithm expression, right? Logarithm term. And the question is write it as one single logarithm. Okay, let's do this. So this is example 1. Okay, so we have log of 5, you see, log of 5 in base 3 plus log of 8 in base 3 minus log of 2 in base 3. So the question is rewrite this as one single logarithm. So first of all, I see that there is addition, right? You see, there is addition. So let's first do this addition. Let's first simplify the sum of these two log. Okay, so it's gonna be log of same base, so we carry the base 3, and then the input must be the product 5 times 8. 5 times 8 is what? 40. So it's gonna be log of 40. Okay, log of 40. Okay, now carry the rest, minus log of 2 to the base 3. So in the next step, we have difference. You see, we should do this subtraction. So the next step is doing a subtraction. So the result is gonna be the log in the same base, carry the number 3, and then the input value should be the division of these two values, 40 divided by 20. So the answer is gonna be log of, so this is gonna be 20, right? In base 3. So the question asks us to rewrite this whole thing as one single logarithm. So as one single logarithm, it can be written as log of 20 in the base 3 using sum and difference property. So we use the sum and difference property in order to simplify this expression as one single logarithm. Now let's do example 2. Evaluate this expression, logarithmic expression, without a calculator. Okay, so let's do example 2. The expression is 2 log of 5. This is common log. You see, there is no base. That means the base is 10. 2 log of 5 plus log of 4. And the question asks us to evaluate this in a sense that without a calculator, by first rewriting as a single logarithm. Okay, so first of all, as a single logarithm, this is gonna be, so it says without calculator. Okay, so let's see. This is gonna be 2 log of 5 plus log of 4 is 2 square, right? 4 is 2 square. However, here I have addition, right? So when we have addition, because it says first write it as a single, maybe because it says first write it as a single logarithm, maybe I go with the summation. You see there is a summation. We first add these two terms and then start simplifying. But before adding, I see that I have a multiplier here, so I cannot go ahead and multiply. I first need to get rid of this multiplier. How can I get rid of this multiplier? Recall the formula that this number can either sit as a multiplier when you have a multiplier for logarithm, or it can sit as an exponent. So I can rewrite this. So the first step is to rewrite this. This is gonna be log of 5 square plus log of 4. You see that? So that 2, the value 2, that is that sits as a multiplier for the logarithm function, we can move it and put it as an exponent for the input value. Okay, so this is gonna be log of 25 plus log of 4, right? Now we can do the addition. Now do the addition and add these two logarithms. So it's going to be log of 25 multiplied by 4. 25 multiplied by 4 gives me 100. So it's going to be log of 100. You see, so we just did the addition. Now we can simplify it. Why? Because log of 100 is 10 square, right? And then again, 10 is exponent, so it can come and sit as multiplier. So it's going to be log of 10. So what do I have here? Recall that when there is nothing written as the base, that means that's a common log. The base is 10. So I have the log of 10 over 10. Recall that this is 1, the first property we learned today. So this is 1. So the answer is 2 times 1, which is 2. Okay. So we first simplify this as log of 25, then we do the addition, we get log of 100, and then we recall that 100 is 10 squared, so this gives us the 2. So without calculator, we were able to do that problem. Now let's look at example 3. Example 3. We are given natural log expression. So we are given this expression, and the question is rewrite it as a sum or difference of log. Okay, so we are given natural log of, and then here we have x to the 4 times y divided by 7. This is the input for this natural log function. And the question is rewrite this either as the sum or difference of logarithmic function. Okay, so I see the first thing that catch my eyes is this division. Because I remember that we learned that division, we just saw, let me show it to you here. We just learned that division, we have this property that when you have log of a division, that can be expressed as the subtraction difference, right? So I'm going to use that property to rewrite this division as a subtraction. So we are using the difference property. So it's going to be natural log of numerator minus natural log of denominator. So what is this? This is difference property, logarithm difference property. Okay, so that's the first thing that I see. Now let's see if we can simplify further. So what do I have now? I have natural log of x to the 4 times, you see here I have multiplication. For the input, we have the product, the multiplication of two terms. That reminds me as the first property that we learned here, sum. So when you have the product of, when your input is a product of two values, that can be written as the sum of two logarithm functions. So now I'm gonna use the sum property to rewrite this guy, okay? So here I'm gonna write this as natural log of x to the 4, because it's x to the 4 times, so it's gonna be sum of plus natural log of y. So this is sum property for logarithm function, and then we carry the rest, natural log of 7. Okay, so the first line we use the difference property because the input of the function is a division, so we can express it as the difference of two logarithms. In the next step, we saw that now here here, we saw that here we have the input to be the product, the multiplication of x to the 4 times y. So now we can express it as the sum of two logarithms. The final step to simplify it is just here I see natural log to the 4. So now I can use the exponential for property that when you have exponent, when your input, when the input of logarithm has exponent, that can come and sit as the multiplier. So this can be written as 4 times natural log of x. And then we carry the rest plus natural log of y minus natural log of 7. Okay, so that's it. So we wanted to rewrite this as the sum and difference of log. This is the simplest for 4 times natural log of x plus natural log of 7 minus natural log of, 4 times natural log of x plus natural log of y minus natural log of 7, which is the same as we got here. Okay. So as you can see, you can apply these properties to rewrite expression. Now let's see how can they help us in solving equations that involves logarithmic function. Our main goal, recall that our main goal is to solve equations that contain exponential or logarithmic function. So we are looking at example 5. Okay, so we have solve, this is the equation, log of, what is the input? The input of this logarithmic function is 2x minus 6. So this is the input of the log. The base, this is a common log. When the base is not written, you see, when the base is not written, that means the base is 10. Okay, so when we don't, if you ever see a log without any base, that means the base is 10, equal 3. Okay, the question is solve it for x. So if I'm going to solve this, the first thing is that comes to my mind is that we can rewrite this as exponential function because this is the base, right? Recall that you can rewrite this as base to the exponent. So this is the, in terms of exponential function, this is going to be the exponent. So it's going to be 10 to the exponent equals, then it should be equal to this, whatever is the input, which is 2x minus 6. Okay, so the first step is we rewrite this logarithmic equation in the forms of exponential equation. Okay. And then we solve this, the next equation, and then we are here. We should solve this. This is algebra, right? Because I know 10 cube is 1,000. I mean, we can do the rest. 10 cube is 1,000. Then we have 2x minus 6. So that you know how to solve equation like this in algebra. You add 6 to the both side, and then you divide both sides by 2. Right? And then you solve it, and then that's it. That's x. If you want to go further, you say 1,006 divided by 2, 503. That's x. See? So the only, new part was to rewriting this logarithmic function in the terms of exponential function. The rest is just simple algebra, as you can see. Okay. Okay, and in your textbook, I encourage you to read your textbook. It shows 2 methods. Let me see. Yes, the first method is rewriting as an exponential, which is what I did. I rewrote the equation in terms of exponential function, and I was able to quickly solve it. Let's see, what is the next method? The next method is, oh, I see. Yeah, that's also possible that you Yeah, but I think, I don't know, I feel like this was easier. I think the first method was easier, but there is also another method. If you like, I encourage you to read over it. So now let's look at example 6. Example 6. Question is solve this equation for x. So what is this equation? It's the difference of two logarithmic function. The first one is log of 50x plus 25. So we have log of 50x plus 25 minus log of x equal to. So the question is solve it for x. Solve it for x. So find the x value that satisfies this equation. So as we can see, this equation contains logarithmic function. So we need to use the properties of logarithmic function in order to solve it. If this was one single logarithm, then I could easily rewrite it as the exponential function, but it's not. It has two logarithmic functions. So, but we learned a way to express it as one single logarithmic. Look, this is a difference. This is a subtraction, and we learned that we can use the difference property. So here I am applying logarithmic difference property that says when you have subtraction of two logarithms, it's gonna be the logarithm of division of those two inputs. So it's gonna be division. Is it subtraction or addition? Sorry, just need to quickly check. Yes, that's subtraction. So it's gonna be division of 5x plus 25 divided by x. Okay, so equals 2. You carry the rest. So the first step is I see the subtraction of two logarithmic terms. Using the sum, using difference property, we can rewrite it as one single logarithm, which is gonna be logarithm in the same base, but the input is gonna be the division of these two input values. Okay. Okay. Now the next step is now that we have one single logarithm, now we can rewrite it. We can rewrite it in exponential format. Exponential as the exponential equation or exponential format. How can we do that? Recall that. What is the base? Base is 10. So it's gonna be base, recall, to the power of this. So it's gonna, we can rewrite it as 10 to the power of 2 equal whatever is right here, which is 50x plus 25 over x. So what you see here is just the same relationship, but instead of logarithmic, we are expressing that relationship in terms of exponential. Okay, the rest is just algebra. Look, 10 squared is 100, right? And here we have a fraction. So now the rest is easy. We know from algebra how to solve this. So cross multiply, it's gonna be 100x times equal 50x plus 25 times 1. And then we can group the extra stuff. So it's gonna be 100x minus 50x equal 25. So 50x is 25. So x is 25 divided by 50. So x is half. See? This is the big picture of how we got here. Right? You can also check the work in your textbook that prefers rewrite this difference, this subtraction of logarithm as a one single logarithm. Then we rewrite it in exponential form. We get to here, the rest is just algebra. Okay, let's now look at example 7. It says, again, solve an equation. This equation contains 3 natural log expression. Okay. So, example 7. So it has the left side of equation is natural log of x plus 2 plus natural log of x plus 1 equal natural log of 4x plus 14. Okay? And the question is solve it for x. Solve it for x. Find the x value. Find the value that satisfies this equation. Okay, so let's first see if we can apply any property. So we learned about the sum property. By sum, we mean addition of 2 logarithmic functions. I have one logarithmic function here, one logarithmic function here, and we have their summation. So we can use the sum property, property in order to rewrite this. This is going to be natural log of what? When you have addition, then you multiply those 2 expressions. So it's going to be x plus 2 times x plus 1. And then you carry the rest. Equal natural log of 4x plus 14. So let me first do this multiplication, because here, as you can see, we need to multiply, we need to expand this. So this is gonna be x squared and then 2x 1x is 3x plus 2. And on the other side, we should have this, right? So far, the only thing we did is just applying the sum property. The sum property says that when you have the addition of 2 logarithmic functions, it's going to be the same as one single logarithm, but you need to multiply those 2 input values. So we multiplied x plus 2 by x plus 1, and we got x squared plus 3x plus 2. Okay, now what then? What's next? So we have this equation. On the left side, we have a natural log. On the right side, we have another natural log. They have same base, but so they must be the same, right? We have this equality, and on the left side and right side, both of them we have natural log. So both of them have the base b. So if they have the same base, these logarithms, so that implies that we should have the same inputs. Or even if you don't see that, you can, yeah, I think you can see that. Let me see. I believe it's not difficult to see that these 2 must be equal. Because if the reason is that the function is 1-to-1. The reason is that because look, here we have the situation that we have 2 output values, and my argument is that, okay, if these 2 natural log, if this and these are the same, so these are the output values. If these 2 functions are the same, then they should have the same input value. However, that's not correct when you have for example, this is not one-to-one. You have two different input value and you have the same output value. But recall that both logarithm and exponential function are one-to-one. So since these functions are one-to-one, then each output value corresponds to a unique input value. So we can make this conclusion here that since these two outputs, I'm going to put it this way, since these two outputs are the same, so their input value must be the same. Okay, so then the rest is algebra. Let's take everything one side. So we subtract both sides by 4x and 14, and then we group the similar stuff. For example, x squared is by itself, but we have 3x and negative 4x, so that's gonna be negative x. 2 minus 14 is gonna be negative 12, right? And then we can factor this, right? Because we want to solve it for x. So how about two values that the product is 12, the subtraction is negative 1. So we can factor it in this way, because x squared, and then we have 3x negative 4x, it gives me negative x, and then plus times minus is negative, 3 times 4 is 40. So that the factorization is correct. So now we have either x plus 3 is 0, or x minus 4 is 0, right? So this gives me x equal negative 3. This gives me x equal 4. So we came up with two x values, right? We end up with two x values. So now let's see. If you substitute, so look at this. So one of them is negative 3, the other one is 4, right? But look at the equations. So for example, if I put the negative 3 here, I'm going to end up with natural log of negative 3 plus 2. If I put the negative 3 here, right? So this is going to be natural log of negative 1. What's the problem with this? The problem is that logarithmic function only take positive value. Why? I'm going to quickly remind you of this. Look, you have exponential function, right? Recall, you have b to the x, the exponential function. It takes you an input value. For example, suppose you have 2 to the x, right? So it takes input value x, it calculates 2 to the x for you, and it returns you the output value. So recall that no matter what is the input value, the answer is always positive. So for example, if it is 2 to the 1 is positive, 2 to the 2 is positive, and so on. Or even if 2 to the negative 1 is half, 2 to the negative 2, it's 1/4, 2 to the negative 5. So no matter what is the input value, the output value is always positive, right? The output is always positive. Now think about logarithmic function, like natural log of x. Recall that this is just, logarithm function is just the inverse. Sorry, let me correct it. Recall that logarithm, right, is just the inverse log, is just the inverse of exponential function. So what it takes is this output, right? So since these outputs are always positive, that means logarithm only can take positive value. So the domain of logarithm function is all positive numbers, all positive value. They cannot take any negative value. So for that reason, I cannot, this doesn't make sense, because the input cannot be negative. We don't have that. We don't have the negative one. So for that reason, we cannot accept this not acceptable. We cannot accept the answer -3. So I'm gonna say this one is not acceptable. But 4 is okay. 4 is positive, and when you substitute 4 into, let me show you the big picture. When you substitute 4 into any of this logarithmic function, it's going to end up with an input positive. So this one is okay. This is acceptable. So what is the final answer? The final answer is 4. However, when we did the algebra, we end up with two solutions, -3 and 4. But we cannot accept -3 because logarithm function do not take input negative input values. They only accept positive input value. So for that reason, we can only accept 4. And you can also look at the argument in the textbook. So I think we had pretty enough exercises, practices on this, but yeah, technically you already know the definition of logarithmic. It's just playing and practicing the properties, the inverse property, exponential property, sum and difference, especially using sum and difference of logs property. For what reason? To be able to solve equations using log rules. These are good exercises. I recommend you to try these in order to practice. And now I think you should be able, you should be ready to do the exercises of this section. Thank you for watching this video. I'll see you in the next one.